we have Tyler Powell, whose presentation is titled Modeling Ice Stability in Small PSRs with 3D Heat Conduction. Over to you,
Cool.
Tyler.
Hi, can you hear me?
Yep, loud and clear.
Cool. So yeah, I'll be talking about the thermal environments of small cold trap craters. Next slide. So craters and other topography near the poles can be shielded from solar illumination year-round. And several studies suggest the presence of ice in these PSRs. These are really interesting locations, but the lack of illumination may introduce several challenges for exploration, particularly for large PSRs. So one solution that we thought of is that we might be able to sample ice from smaller cold traps, which are easy to navigate, maybe on the scale of a few meters or tens of meters. So I'm showing an Apollo image here, but you can imagine that if this mission were at their poles, there would be plenty of easily accessible cold traps to study in the area. However, one issue with this is that the temperatures in small PSRs may be influenced by lateral heat conduction, and at some scale, this will destroy a PSR's ability to cold trap. So the question we were interested in is, what is the smallest possible thermally viable cold trap? And what is the subsurface thermal environment of a small cold trap? To look at this, we used a 3D thermal conduction and surface illumination code that we've been developing. And we modeled two different size craters and depth of diameters at a latitude of 85 degrees. Next slide. So this slide shows model results for the temperature of the PSR throughout the day for a 50 centimeter and 1.5 meter crater. Even though the shadow never receives direct solar illumination, there is an increase during the daytime because of scattered light from the opposite wall. Our results can be compared to the Ingersoll temperature, which is an analytic solution for the radiative equilibrium temperature of a shadow in a bowl-shaped crater. And this is kind of a lower bound. So if our subsurface conduction is supplying any additional heat, this will result in higher temperatures. So our results show that shadow temperatures are slightly higher than the Ingersoll temperature, but not by very much. And also, as expected, the smaller cold trap is also slightly warmer than the larger one, but also not by very much. So even for a crater as small as 50 centimeters, lateral heat conduction isn't significant enough to noticeably change the temperature of the PSR. So craters of this size and larger should still be viable cold traps, which is pretty cool. Next slide. This slide shows the maximum surface temperature and subsurface temperature experienced throughout the day. The top two plots are of a 1.5 meter crater, and the bottom one is of a 50 centimeter crater. What these results show is that the higher average temperatures outside the cold trap basically fill in around the lower PSR temperatures, and the cold trap temperatures of the PSR only propagate to some depth. On each, we have a 120 Kelvin isotherm, indicating an approximate threshold for cold trap stability, and in both cases, the depth of the isotherm is roughly proportional to the size of the crater. This is about 20 centimeters for the 1.5 meter crater and about 7 centimeters for the 50 centimeter crater. As long as the surface temperatures are the same, this geometry should basically be independent of scale. So a 100 meter crater should have cold traps extending down to maybe 10 meters or so. Though, of course, this will break down at some very small size once the surface temperatures are no longer the same. I think this also shows why a 50 centimeter PSR is thermally stable. So most of the change in temperature between the surface and depth occurs over a scale of maybe 10 centimeters or so. Oh, okay. And given the low conductivity of the regolith, this isn't large enough to warm the cold trap faster than it's able to radiate away this heat. Next slide. So one issue that we ran into when thinking about this is that sampling a small crater is the fact that small craters tend to be younger on average. So this may limit the amount of volatiles which would have had time to accumulate. So here we estimate the age of craters of various size. Basically, the oldest a crater can be is approximately the time it takes to reach saturation equilibrium at that size. Any craters which are produced before this time would have since been erased by a newer one. And from this, we see that a 1 meter crater is likely to only be about 10 million years old, while a 100 meter crater can be as old as 1 billion years or so. So it may be possible to find some surface frost deposits in these smaller craters, but in general, there's likely some trade-off between the accessibility of small craters and the time that they've been able to accumulate volatiles. Next slide. So I'll kind of leave it here. Our general conclusions are that even really small craters, like 50 centimeters or so, are still thermally viable, and that the reduced surface temperature extends to a depth that's proportional to the scale of the PSR. But there's likely some trade-off between size and crater age. I'll stop there.
All right, excellent, Tyler. Thank you for finishing early and still giving an excellent talk.